The temperature of lava in a volcano at time t is modeled by a strictly increasing, okay, good to know, twice differentiable, we might need that information later, function called L. L of t is, okay, now we're about to get to the nitty-gritty of what it is. L of t is measured in degrees Fahrenheit. So the output of L, the function that tells us the temperature, is Fahrenheit. T is measured in hours. This is not Fahrenheit per hour. That's just Fahrenheit for L. Values of L of t at selected times of t for the first 24 hours after measurements began, given in the table below. For 24 to 48, the function L that models the temperature of the lava has a first derivative given by this. Oh my, what are we going to do? Well, we're just going to keep on moving. That's what we're going to do. Use the data in the table to evaluate the integral from 0 to 24 of L prime of t. Oh, okay, I can do this. Let's grab the appropriate colored pen. Guess which color I grabbed? You are correct, if you said purple. I'm just writing some stuff. Interpret its meaning using correct units. Okay, so this is a function that is the integral of L prime. We are going to take the antiderivative of a derivative and it just gives us L. And that is evaluated at 0 and 24. And we'll plug them in. So we need L of 24 minus L of 0. 24, L of 24 is 2814 degrees Fahrenheit. Let's put that in there. You don't have to put it here, but let's put that in there. Degrees Fahrenheit. Minus L of 0, which is 2454 degrees Fahrenheit. And that gives me, when I subtract them, 360 degrees Fahrenheit. Okay. Interpret its meaning using correct units. Okay, L prime would be the rate of change of the Fahrenheit, the degrees Fahrenheit. So this is really degrees Fahrenheit per hour. But we had discussed this in a previous lesson, that if I am finding the area under a curve, or you're not finding the area under a curve, I know, I get it. But if I'm finding the area under a curve, or also known as an integral in this case, I am going to find a quantity when given a rate. This is a rate that they really didn't discuss up in this first couple sentences here. So we have a rate, the integral of a rate, antiderivative of a rate gives me a quantity. Quantity is this many degrees Fahrenheit. Okay, interpret its meaning using correct units. For the first 24 hours, the temperature of the volcano increased, because this is positive, by 360 degrees Fahrenheit. I'm going to write that as a sentence. For 0 to 24 hours, that's a perfectly legitimate way to write it, the temperature of the lava, lave, that means to wash, lava in the volcano rose 360 degrees Fahrenheit. Now, I know you're probably thinking, well, I could have just subtracted those and gotten it. I hear you, but we need to understand this representation and what it means. Okay, determine the temperature of the lava at T equals 48 hours. So I want you to think about this. Guy walks up to a volcano, starts measuring the temperature. I don't think it's a smart thing to do, but whatever. He walks up to the volcano and starts measuring the temperature. At the end of 24 hours, this is the temperature of the volcano, okay? So this is our starting point. This is the temperature at the end of 24 hours. We want to go 48 hours. We don't have enough information here. Maybe they gave us some clues. So here's what's going to happen. We are going to start with a temperature of 2,814 degrees Fahrenheit. And then we're going to add some more temperature. How much more temperature? Let's find out. What I want to do is find out how much more temperature was added from 24 to 48 hours. How am I going to find the quantity? I'm going to take the integral of the derivative there, okay? Again, I start here. I measure the thing for 24 hours, then I say, oh man, I don't have any more data in my table. I just need to keep going. Well, how do I keep going? They gave me the derivative of L, so I could keep going, because the integral of the derivative will give me what I need, okay? Now, things are about to get a little bit wacky. Before they get any wackier, let me label on paper what I just said. This is the temp at 24 hours, and all this right here is the change in the temperature, which is going to be positive. Why do I know that? Because they said so. Change in temperature for hours 24 to 48. That's what this represents. If I know where I'm starting at 24 hours and then I add the change, I'll get the rest of it. So we are tempted, based on the rest of this lesson, to write it out a little bit differently. I'm going to put it on the bottom of the paper. You don't have to write this. So here we go. I would have 2814, I'm still running out of ink in this pen, times, or plus the integral 24 to 48 of e to the sine of the square root of x dx. That is L of t dt. Oops, there's a little typo here. That should say sine of t. There we go. Sine of the square root of t. So that should have t's there, not x's. Okay, sorry about that. Little mistake. Then we would say, oh, what's the antiderivative of e to the sine of the square root of t? E to the sine of square root of t. Yeah, good luck. Good luck with that. Yeah, really good luck with that. That is, as far as I know, not possible. It might be possible, not with our tool set, not with the things that I have learned and recall. So it is time that you learn something really cool. Here we go. Check this out. L prime is going to go in my calculator. I will use x instead of t though. So let's start with that. So whatever you have, type it in. Clear it out, type this in. Sine, we are in radians, and we should be. Square root of x, not t, just because of what we're doing. So there we go. Well, you could use t if you wanted to. I choose not to. So we now have that in. It is in y1. We're going to press quit. All right. This problem starts, well, we have a starting point of this. Plus what? The integral. We can figure these out on a calculator. Do we always need to do that? No. First of all, we need to know the skills. Second of all, it's not always going to work depending on where the variables are. But in this context, it totally will. So actually, before I type anything else on the calculator, we'll just type it in the way it is down here. Math. Press math. Do you see something that looks like a integral? I believe it's number 9. The function integral. It's number 9. Everything you need at this point is right there. So 24 to 48 of this function, which is y1. I could go back up here if I wanted to. Alpha, trace, pull up y1. Now, my function is defined with x in the calculator. On paper, it's defined with a t. Either way, just be consistent with what you're doing. And takes it a minute, and there you go. So hopefully you're realizing what's happening here. Let me write down the final answer. 2,835 point, always 3 decimal places in this class, 0.054. Let's put degrees Fahrenheit because that's what it is. I hope you noticed what just happened. We just, very little bit, gained just a little bit of temperature in the next 24 hours. So we started at 2814 and then we added just a few more degrees Fahrenheit. It doesn't get too much hotter. When you're that hot, it just, what's an extra 21 degrees, right? So just FYI, math 9, you don't have to type this, but 24 to 48 of your function, alpha, trace, pulls up y1. And so This is how much temperature was added from hours 24 to 48. So we started that hot and then added that much more. There it went.